So let us recall what we have did in the previous lecture. In the previous lecture, we have discussed about the compact matrix space. So X is a compact if and only if we have stated certain results. The first one is X is totally bounded and complete. The second result we have did it is if and only if every sequence in X has convergent subsequence. And third results we have discussed is that every open covering of X has finite subcover. That means if X is covered by a family of open intervals Gi, then X can be, then there exists some finite family of this open sets, so that this X is covered by that many finite members of this family. So we have proved in the previous lectures these three inequalities, in that we have assumed that this is as a definition, that is X is compact, then it is totally bounded and complete, and based on that we have proved this two statements. Here in this lecture we also discuss one more property, is known as finite intersection property. So let us first of all understand what do you mean by finite intersection property. A family script F of subsets of X is said to have a finite intersection property if the intersection of any finite number of sets in script F has is never empty. Is never empty. That means if you can write down this is in the notation form, then this says that for every family, well, any family is there, and so the script F is a family of subsets of X. That means for every finite collection, that is F1, F2 up to Fn, belongs to F, script F, such that this intersection of this F1, F2 up Fn is always non-empty. This is known as finite intersection property, and this is true for any n. If you can pick up any n, then in this family, so if you can pick up any subsets of this family, any elements of this family, if you make intersection of them, it will always non-empty. That is known as finite intersection property. Let's have the example of such family. Let us consider this script F as a family of open intervals, that is 0 to 1 by n, where n belongs to n. Now this family, so this is a family of open intervals, or I can say it is a class of open intervals, and it is given by this. So what are the sets in this comes? Let us see geometrically. So this is 0. The first one is when n is 1, then it is 0 to 1, and then it will be 1 by 2. So the first interval is 0 to 1, second interval is 0 to 1 by 2, the third interval is 0 to 3, 1 by 3, and so on. So this is your F1, or in this particular case, we will have certain subset open intervals. Now we have to prove that this script F has finite intersection property. We shall show that the script F has finite intersection property. That means if you can pick up any finite member of this family, and if you take the intersection of them, it is always non-empty. So for that, I will pick up this intervals. Let's say it is 0 to b1, intersection with 0 to b2. If I make the intersection of all these intervals, up to it is finite number, 0 to bn. So ultimately, I am picking up any of this set type. That means maybe this is b1, I don't know. Maybe the next 1 upon 10,000 or 100 is there, will be b2, and so on. Whatever the number you can pick. This is any random numbers, b1, b2 up to bn is there. So this bi is of the type 1 upon n. Okay, or any of this value you can pick, for any n belongs to n, it may pick this value. Now what will be the intersection of this? The intersection of this will be always, you can just see that whatever the minimum number, that is this b1, b2 up to bn is there, whatever the minimum number is there, that is comes to an intersection. So this intersection is always 0 to b, and which is non-empty, where what is this b? This b is actually a minimum of this b1, b2 up to bn. That is obvious. Suppose bn is 10,000 or whatever the number is, but whatever the number is the smallest out of this b1, b2, bn, that should be the intersection of this, all this intervals. So hence we can say that the script F has finite intersection property, because you can pick up any of this intersection, it is always non-empty. It is always in one interval. So therefore we can say that the script F, which we have defined here, has finite intersection property. Let's say another example. The family of closed intervals you can pick up the script F as set of all intervals, closed interval -1 by n to 1 by n, where n is belongs to n, has a finite intersection property. That also you can see easily, because this intervals, when n equal to 1, it will be minus 1 to 1. It is a closed interval from minus 1 to 1. The second interval is minus 1 by 2 to plus 1 by 2. The third interval is so on. So it is the same argument we have given here. You can give the same argument for this family also. So this will also has finite intersection property. Let's take another example. Let us consider this family. Consider script f as minus infinity to n, where n belongs to z. If you consider this family, then this family also has the finite intersection property. Finite intersection property. That also you can prove in the similar manner. So all these sets have the finite intersection property. Now, what will be the relation between this finite intersection property? Any family will have a finite intersection property and this compact set. Okay. So based on that, we have a next result. And this result says that if X is compact, a matrix space, X is compact, if and only if every family script f of closed subset of X. Here just one word is added, that is a closed subset. With finite intersection property, has itself non-empty intersection. That means intersection of all this f which is in script f, which is non-empty. So it says that if the script f, which is a closed subset of X, with having the finite intersection property, that means if the intersection of the finitely many element or finitely many members of this script f has the non-empty intersection, then this family itself has a non-empty intersection. So that is the result, is equivalent result for the compact matrix space. For example, in this, you can pick up the first one. This, so can I say that intersection of all this 1 to infinity, 0 to 1 by n is non-empty? What will be the intersection of this? Intersection of all these intervals which we define like this. What will be the intersection? Use the nested interval theorem. It is singleton 0. Okay, which is non-empty. Why we have this? Because all of this here they are not open sets. Okay. Here they are open sets, they are not closed sets. So if I have closed interval here, then we can use that national intersection for national nested interval theorem. If I put here closeness, so in this family, if I put the closeness, then we can able to apply this result which we have discussed or we have written here. Otherwise, we cannot apply. For this, we can apply that result. All of them are the subsets of closed interval -1 to 1. All this family. Since this is compact set, we know it is a closed and bounded subset of R. The intersection of all this and this family has the finite intersection property. So in that way also you can prove that this closed interval -1 to 1 is a compact. Okay. So this is another way to looking at the compactness. Let us try to prove this statement. So let us assume first that X is compact. And a script F is a family of closed set has finite intersection property. This is our object, means this we have assumed. What is our objective? We shall show that the intersection of all this F, where this F is belongs to script F, is non-empty. This is our objective. Suppose not, suppose if possible, that intersection of this script F will be empty. Now we'll start with X. X I can write as X minus 5. But X minus 5, pi is this, I can put this value here. By using the De Morgan's law, I can write down this is as union of F belongs to script F, X minus F. If I want this intersection out, then it has to be union. So what we can have is X is covered by this sets, and X minus F, F is a closed set, so X is a complement, X minus F is a complement of a closed set, and we have learned the result as if F is closed, if and only if its complement is open. So if we use that result, and we can say that therefore we note that this X minus F, where F is belongs to script F, so this is the family, is an open covering of X. Why? Because F is closed, implies X minus F is open, and it is already covered X. So that's why this X minus F, this family is open covering of X, and X is compact, and we have learned that result that every open covering has finite subcovering. So since X is compact, there exists a finite number of subsets X minus subsets X minus F1, X minus F2 up to X minus Fn, such that X is covered by X minus Fi, union of this. So it's covered by this. But what will be this gives? So this will implies X minus X is equal to, if I take this union inside then it is x minus intersection of fi. This is set theoretical result which we can easily see. Now x minus something, x minus something. So you have a one set and you are subtracting some quantity from that, and this inequality is there. So equality is there. So that's why we can have this intersection should be empty, which is contradiction with script f has finite intersection property, because we have taken the script f has finite intersection property, but it will violate this result. So therefore, why this we have this contradiction? Because we have assumed that this whole intersection is empty. So we can say that intersection of script f, or sorry, f belongs to script f, is non-empty. This is always there. The converse part, that is this part. Suppose that every collection of closed subsets of x with finite intersection property has non-empty intersection. So this will have a non-empty intersection. What is our objective? We shall show that x is compact. X is compact. This is our objective. So ultimately, if it is, I want to prove that it is compact, I can use any of the result which I have discussed in the starting of the lecture. Either you can prove it is totally bounded complete, or you can prove that it is sequentially compact, which is say that every sequence has conversion subsequence, or you can prove that every open covering has finite subcovering, which is known as Hein-Borer property. Okay, so I will prove that, means I will prove that the last statement, that means every open covering has a finite subcovering. So I will start with one open covering of x. So let Gi be an open covering of x. So therefore what we can have is x is a subset of union of Gi. So ultimately what we can say, it is x minus union of Gi. If I subtract x from this union, it is always empty. And using again by set theory result that this intersection of all this I, x minus Gi, is empty. Now therefore what we can say, this x minus Gi is a, since Gi is an open set, so x minus Gi is a closed set. So this collection, that means this collection x minus Gi is a collection of closed sets with empty intersection. So this is the collection of the closed sets which has empty intersection. That means what we can say is, by our hypothesis, which we have assumed that x minus Gi does not have finite intersection property. Because our hypothesis says that every collection of a closed sets with finite intersection property has non-empty intersection. Here, this family has empty intersection. That means it does not have a finite intersection property. Since it does not have a finite intersection property, therefore there exists a finite number of subsets x minus g1, x minus g2, up to x minus gn, such that this intersection is empty. Is empty. But this will gives you that x minus union of k running from 1 to n, gk is empty. So x minus this quantity is empty, then therefore we can say that x is subset of union of, or you can write equal to, maybe possible. Okay, so therefore this x has finite subcover, which is there. So that means the open covering of this GI has a finite subcovering, and which completes that X is compact because of Einstein property. Okay. Now we have this. Let us recall what we have did till now regarding this regarding this compact matrix space. X is compact if and only if we have proved that X is totally bounded plus complete. The second result, it is if and only if every sequence in X has convergent subsequence. Every sequence has convergent subsequence. The third result, we have proved that it has Hein-Borer property. It's equivalent to saying that every open covering has finite subcovering. Every open covering of X has finite subcovering is there. The fourth statement that we can say is every family of closed subsets X has finite intersection property have itself non-empty intersection. We have proved these four statements are equivalent till now. I am giving you two more statement or one more statement as a project. Somebody can like to prove that, which is given in some of the reference book. For example, in the book of Das and Patnaik, the proof of is already given. That is, if and only if every infinite subset, every infinite set A of X as limit point. So if you pick up any infinite set, in that set will always have a limit point. Also, so these are the 5 results of compactness. Equivalent 5 results are there. That X is compact if and only if it is totally bounded plus complete if and only if every sequence has convergent subsequence if and only if open covering has finite subcovering. Every family of closed subsets of X has finite intersection property will have itself as non-empty intersection, and the fifth one is every infinite has a limit point. In some of the book, they have defined any one of them as a definition, and they prove the other statement. So those who are interested, they can also try to look at in that manner. For example, someone can assume that this statement as their definition, and they may prove that it is totally bounded plus complete. Some of the book they have taken this is as a definition, and they will prove the other statement as a result. So if someone want to prove or want to take a project on that, they can also take it. So use the different reference book, maybe in Munkers, maybe in the G.F. Simmons. In all these books have the different definition. Here our definition is the first one which we have taken. X is compact if and only if X is totally bounded plus complete. And using that we have arrived with this 3 or this 4 statement. Now from other definition you can pick up and you can prove the other results. Okay, that is, so the lots of project I have given here in this talk. Fine.